Hey everyone, my name is Raunak, back with another video. This is 38th video in the Getting Started with the Machine Learning playlist, and in this video you are going to learn the support vector machines. I should have actually covered SVM way before the trees. Instead of boring you with a lot of technical definitions and everything, let me show you an example where let us assume that this is the dataset that you have, where you have green points and purple points. So the most basic classification aspect is passing a line in order to divide the things. So this is the way we would pass a line, obviously, because we cannot pass it like, let's say, this or that way. Alright, we cannot make any shifts or turns in it. This is the most optimal manner in which we can pass the line. But what else do you think you need? So after passing a line, the points to each other, how we are going to determine where the line is going to be there? Okay, so my line can be inclined more towards, let's say, green points, or can be more inclined towards the purple points. So I have to create a margin, an equal form of margin. So right before learning about margin, the line that you see right now, which is dividing the 2 points, is known as hyperplane. This is also known as an optimal hyperplane. Now, like I said, I want to check the inclination of the line. So I need a margin. This is called the maximal margin. So it can be, let's say, any number of points to the left and right, but it is always going to be the same. Alright, so this is known as maximal margin. Now you might be wondering, okay, I'm talking about hyperplane and maximal margin, but what really is support vector machine? Where does this word support vectors come from? As you can see on my margin hyperplane, so you can also call this, so the hyperplane that you see over here, which is touching the green points, is known as negative hyperplane, and the hyperplane that you can see, which is touching the purple points, is known as positive hyperplane. So what really is the support vector in all of this? Support vectors are basically the points that touch these hyperplanes. So this is known as support vectors. Support vectors in the sense, when a point touches the line, I can say that now if any of my classification object falls beyond this line, it is going to be considered the green one. If it falls beyond this line, I can consider it purple one. So the line which passes through all of the points is known as the margin with the hyperplane, and this is known as the optimal hyperplane, the one that you can see. Now let us assume that this is a W vector in the dimensional space where we have to map the hyperplane, because we yet don't know the equation of the hyperplane. So this equation for the optimal hyperplane, so now this is not the equation, but this is the way it is represented. I'll show you how you can calculate the equation. So the equation that actually tells you about the line is W transpose into, so that into is basically a dot product. So W transpose dot product with X, so X is my point, plus B. So this B is an arbitrary number, which can be also termed as, let's say, bias, which is equal to 0. Alright, so W transpose dot product X plus B is equal to 0. This is the equation used to give us the hyperplane. Yet we don't know the marginal distance of it. Similarly, for my positive points, I'm going to say plus 1. So W transpose dot product X plus B is equal to 1. And similarly for my negative values, so I'll say W transpose into X plus B is equal to minus 1, which indicates that plus 1 minus 1 is the margin that I'm going to use in order to stay in touch with all of my support vectors in my SVM. Now let us actually dig more deeper into the equations and try to figure out what is the real way with which we can perform the equation for the most optimal plane. Let us call the points that lie on the positive margin as x1 and x2 for the points that lie on the negative margin. So these margins actually are very important, because if you don't have margin, this is just going to be some another sort of, let's say, classification problem. So SVM was one of the, I would say, greatest achievements ever. So what I can do is I can negate the entire equation, where I can say W transpose dot product X of 1 plus B is equal to 1, which I'm going to subtract from W transpose into X of 2 plus B is equal to minus 1. Now why I'm actually subtracting this? You can see this W vector pointing to a direction. So this X2 and X1 are the 2 points where I want to check where my points in the vector space touch to the margins. So this W is going to extend to a certain point over here, and then it is going to extend to this certain point over here, which are known as x1 and x2. So I am actually trying to find a distance. So this distance is going to be the optimal equation for our SVM. So like I said, W transpose into x of I plus b is equal to 1, and W transpose into x of 2 plus b of b is equal to minus 1 is basically going to get subtracted. Alright, so I am trying to subtract x1 minus x2. That is the equation that I want to find in order to get the distance of that margin, which actually gets calculated to this, which is W transpose into x of 1 minus x of 2 is equal to 2. Now you may ask, how come? So we just cancel out the b's. Alright. So the negative sign over the minus 1 is going to make it positive, which gives us 2. And here W transpose stays the same because it is a multiplied, it is a dot product along with the x of 1 and x of 2. So I take it out as common, and here I say x of 1 minus x of 2. This is not where we stop. We need something more. So the way we are going to do it, I want to remove this W transpose so that I can have the optimal distance or the equation for my SVM. But you cannot just remove a transpose value all of the sudden. You have to use the normal. So when you have the equation and when you normalize it, then you will have a proper equation for your optimal margin of the SVM. So this is the way we do it. So we actually divide on the both sides with the normal. So I actually try to divide W transpose with the W norm into x of I into x of 1 minus x of 2, which is equal to 2 by norm of W. And this is the way I can get rid of the W transpose on the left side. So this is the factor that actually is the equation for our optimal hyperplane stating the margin. So it is 2 by norm of W. But this is also not where we stop. We have to maximize this function. So when we actually maximize this function over the 2 points, so let us say W and B, which are like 2 points I have for my hyperplane, is equal to max of 2 by W norm, where when I want to predict if the value of my y is greater than or equal to 0, it is going to be 1. That is, let's say this binary classification problem where I want to specify the things. So what I'll do is when my y is greater than 0, equal to or greater than 0, I will say the prediction is 1, that is true. And when it is less than 0, I'm going to say it is incorrect. So incorrect basically states false. So this is the way the SVM is done. Now let us have a look at the practical implementation of the SVM. So welcome to the practical implementation. Okay, this is the simple code that I've made for load breast cancer. That is our common data set I've been using since many tutorials, where I say for X and Y, I'm trying to make the use of the pandas. So I'll just run this first. Then in the second thing, I want to split the data. So I'm splitting it with the 20%. And now let us start with the SVM. So here I'll say from sklearn.svm, I'm going to import SVC, which is support vector classifier. And here I'll say model is equal to SVC. After that, I'm going to say model.fit. Alright, where I'm going to feed it xtrain and ytrain. And I have it. Okay, so at the moment, I'm not going to go deeper into the parameters. I could cover this in some another tutorial. Alright, so let us just keep aside the hyperparameters at the moment and stick to the parameters that we have, default parameters. Now here I'll say ypred is equal to model.predict, where I'm going to feed it xtest. Now later on I can say from sklearn.matrix import accuracy score, and I can say accuracy score where I'm giving it the ytest and ypred, and I have it. It says 94%. And now I'm also going to check the score of my model. So I'll say score where I give it xtrain and ytrain. So I'm actually looking for the training accuracy. It says 90. Okay, so there are much modulations in the model because we have a lot of rows. I'll show you how we can use these hyperparameters in the next upcoming tutorials, where we can actually improve the performance of the model. Not great, I would say. Okay, this is just the casual implementation of the support vector machine. I'll also check some another metrics. So I'll say from sklearn.matrix, I'm going to import confusion matrix, and here I'll say confusion matrix where it takes ytest and ypred. Alright, so we have a lot of misclassifications over here, but other things seem fine. So you can have this notebook in the description box below along with this presentation that I've shown you. And this is it for this tutorial. We are actually going to even look at more insights about the SVM. This is not where we stop. All right, this is just the basic intuition in order to get started with the support vector machines, but there are a lot of aspects to be covered when it comes to SVM. You cannot just cover that in a single video. All right, so if you like my content, please do subscribe to my YouTube channel and click on the bell icon so that you don't miss any of the updates. And thank you for watching. Goodbye.